Welcome to the 5-minute summary of stress, strain and Young's modulus. Remember, you can pause the video at any point or skip back to help complete your notes. Let's begin with stress. Whenever we apply a force to a material, we create a stress within that material. Stress is defined as the force per unit area. We give stress the symbol of sigma, which equals F over A, where F is the force and A is the cross-sectional area. The units of force are newtons and the units of area are meters squared. This means stress has the units of newtons per meter squared, or more commonly, Pascal. We are usually considering the stress acting within a metal wire. This means that the cross-sectional area is pi times the radius squared. Moving on to strain. When we apply our force to a material, if the material extends, we are creating a strain on the material. The strain is defined as the ratio of extension to original length. We give strain the symbol of epsilon and is equal to delta x over x, where delta x is the extension and x is the original length. Both extension and original length have units of meters. This means strain has no units. Strain can be expressed as a percentage. It's useful to remember that the extension is equal to the final length minus the original length. Stress and strain can both be tensile or compressive. Young's modulus. Young's modulus of a material is the stiffness constant, similar to the spring constant. However, it's not affected by the area or the length of the material. It's defined as the ratio of tensile stress to tensile strain. We give Young's modulus the symbol of capital E and is equal to sigma over epsilon, where sigma is the stress and epsilon is the strain. Stress has the units of Pascal and strain has no units, so Young's modulus has the units of Pascal. We can substitute our formula for stress and our formula for strain into our Young's modulus formula to get this expanded version of the formula. Let's have a look at a stress-strain graph for a material such as structural steel. There are 5 main points you need to know on this graph: the limit of proportionality, the elastic limit, the yield point, the ultimate tensile stress, and the breaking point. The limit of proportionality. Above the limit of proportionality, the stress is no longer proportional to strain. We can see this on the graph. Below this point, the graph is a straight line. This shows stress and strain are proportional. Above this point, the graph curves. This shows stress and strain are no longer proportional. The elastic limit. This point is usually above the limit of proportionality. Above the elastic limit, the material will no longer return to its original dimensions when the load is removed. Below the elastic limit is considered the elastic region. This is where elastic deformation happens. Above this point is considered the plastic region. This is where plastic deformation happens. Plastic deformation is when the material is permanently deformed and will not return to its original dimensions. The yield point. At this point, the material's atomic structure changes significantly. This creates a large increase in extension. The ultimate tensile stress. This is the maximum stress the material can take before breaking. It's considered the strength of the material, and the higher up the graph this point is, the stronger the material. Breaking point. This is the point at which the material breaks. Stress-strain graphs will vary depending on the material. Here's two examples. For a brittle material, the graph is a straight line, with perhaps a slight curve at the top. The graph does not exceed its elastic limit. In this case, the ultimate tensile stress and the breaking point are at the same point at the end. A brittle material is one which breaks with little or no plastic deformation. Both glass and cast iron are good examples of brittle materials. Here is the graph for a ductile material. You can see it's much more curved and it does exceed its elastic limit. A ductile material is one which will deform plastically before breaking. Copper and lead are good examples of ductile materials. For any of these graphs, we can find the Young's modulus by calculating the gradient of the straight section of the graph. Thank you for watching our video on stress, strain and Young's modulus, a 5-minute summary. For more videos, follow the link below.